Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our discussion of AP Physics 1 Unit 6, which is on the energy and momentum of rotating systems. And so in this video, we're going to dive right into a little practice problem on collisions with rotational motion. So before we dive into this gross pile of word soup that I have hidden at the bottom of my board here, I want us to review just a few important concepts that may or may not come up later in this video. So first of all, I want us to keep in mind the conservation of angular momentum. The angular momentum that we start out with has to be the same as the angular momentum that we finish with. That is a fundamental law of the universe, and we cannot and will not break it in this AP Physics class. Now, also, another little factoid for us to remember is that the moment of inertia of a point mass is equal to its mass times the radius squared, where that radius is not the radius of our object, but the distance between our point mass and the axis of rotation. Okay, then also we know that the moment of inertia of a disk is 1/2 mr squared, that our linear velocity at any point is equal to the radius between, or distance between where our object is and axis of rotation, times our angular velocity, and that our angular momentum is equal to our moment of inertia times our angular velocity. Now, before we begin, let's expand a little bit on that angular momentum and see if we can find a way to express the angular momentum of a point mass. So we know that the angular momentum of a point mass is going to be equal to the rotational inertia of a point mass times its angular velocity. We know that we can represent the angular moment of inertia of a point mass with this expression mr squared. So I'm going to sub that in here. And then we also know from this little equation here that our linear velocity is equal to our radius times our angular velocity. I'm going to solve this by dividing both sides by r. So I have that my velocity divided by my radius is equal to my angular velocity. Now I have an expression that is the same as my angular velocity, so I'm going to substitute this in for my angular velocity here. So times v divided by r, which means I have r divided by r, those are going to cancel out, and I'm just left with m times r times v for the angular momentum of a point mass. Okay, now I'm going to write this smaller and like up over here on the side so that it doesn't get in our way, but we're going to need this later. The angular momentum of a point mass is equal to m times r times v. Okay, there we go. Now I think we have enough tools for us to be able to dive into this pile of word soup at the bottom of our board here. So we have a 15 kilogram disc with a diameter of 0.8 meters that is rotating counterclockwise with an initial angular velocity of 45 radians per second. Okay, let's pause. There was a lot of useful information in that. Okay, we know that our disk weighs 15 kilograms. I'm going to write that down. The mass of our disk is equal to 15 kilograms. Okay? We also know it has a diameter of 0.8 meters. That means the radius of our disk is half that. So the radius of our disk is equal to 0.40 meters. We know it's rotating counterclockwise, so in the positive rotational direction, with an initial angular velocity of 45 radians per second. 45 radians per second is the initial angular velocity of our disk. So that is just 45 radians per second. Okay, then we have a 5 kilogram clay ball that is traveling at 12 meters per second towards the disk. Okay, I'm going to write down a couple more pieces of information. We know that we have a 5 kilogram clay ball, so now we have the mass of a ball for some reason that's equal to 5.0 kilograms. And we know that it has a velocity, originally, of 12 meters per second. And that's a linear velocity. Then we're told that the ball collides with the disk at the rim and sticks. Okay, so they go from being two separate objects to sticking together and acting like one cohesive thing. Okay, and then we're asked to find the angular velocity of the disk and ball after the collision. Oh goodness, that's a lot. Let's see if we can break that down. Well, we've already pulled out a lot of important numbers and values that were given here. But also, I want to talk for just a second about what this word tells us, this sticks word. We know that they stick together, and now our ball and our disc are traveling as one cohesive system. So that means that they have to have the same angular velocity. So that is very important for us to know. Okay, and we're trying to find out what that angular velocity is. So what is our angular velocity? That's what we're trying to figure out here. Oh, and then I have a little picture just so that we can visualize a little bit better what's going on in this problem. I'm a very visual person, and oftentimes in physics, when you're given a big pile of word soup like I gave y'all here, it's often so much easier if you just draw a little picture so you can see what is actually going on here. So we have a little disc, it's rotating, it's going on its merry way. Then we take a clay ball and we throw it. It sticks to the side of our disc, and then they continue rotating as one. So we can expect that the angular velocity that we start with in our disc is going to speed up as we hit the disc and kick it a little bit faster into motion. Okay, now let's start working out how we might solve this. I'm going to erase all of this so that I have a little bit more room. Now that I have written down the important pieces of information from it, let's just see here. Okay, so we're going to start out here with the conservation of angular momentum. We know our initial angular velocity, we're given a lot of information to start out with. We know that final angular velocity is what we're trying to solve for, and we know that angular velocity is a part of angular momentum. So that's going to be useful for us here today. So if our initial angular momentum has to be equal to our final angular momentum, well, our initial angular momentum that we have is just equal to the sum of the angular momentums of all of the different pieces that we have here, right? So we just have the angular momentum of our ball plus the angular momentum of our disc at the start. And we know that has to be equal to the angular momentum of our ball at the end plus the angular momentum of our disc at the end. It's the wrong letter. At the end. Okay. Now, you might be thinking, okay, yeah, but Beth, our ball isn't rotating at the start, it's just flying in a straight line. It doesn't have angular momentum. That's where I would tell you, unfortunately, that you would be wrong to say such a thing. So it feels weird that an object traveling in a straight line would have angular momentum, but think of it this way. We know angular momentum is always conserved. How can I have something that's traveling in a straight line hit something else and cause it to spin faster? I can't spin my hand that way. Traveling in a straight line hit something and cause it to spin faster, giving it more angular momentum if it didn't have any to start out with. So this is something that's a little counterintuitive, but things traveling in straight paths can have and do have angular momentum because they have the ability to cause rotation. So that's kind of counterintuitive. It feels really weird, but we're going to keep working with it for a little bit and it'll start to feel more comfortable as we go through this unit. For now, just accept that it is how it is. I'm sorry, I can't change it. I don't know that I would if I could, but we do have angular momentum in our ball at the start. So the angular momentum that we start out with, well, our ball, we're going to be treating it as a point mass. We solved for the angular momentum of a point mass right up here. So this is just going to be the mass of our ball times some radius times its velocity, the velocity of our ball. Now, a quick note, this is from right before we hit the disc. So this radius is the distance between where our ball is and the axis of rotation, which is the radius of the disc. It's not the radius of the ball. I know it's a sphere and spheres have radii, and so that's confusing. But this r here is referring to how far away our mass is from where that object is rotating. So that's what this means, and that's the r that we need to be using, the radius of the disc. I'm gonna put the radius of the disc there. Okay, thankfully the initial angular momentum of the disc is much easier. That's pretty standard. We just have the initial, the rotational inertia of the disc times its angular velocity. So this is of the disc times its velocity of the disc at the start. But we know what our rotational inertia is because it's a disc, so I'm just going to rewrite that now. That's 1/2 mr² where m is the mass of the disk, r is the radius of the disk, times the initial angular velocity of our disk. Okay, so that's the left side of our equation. Now we have the right side. We have the final angular momentum of our ball and our disk. They're going to be very much the same thing. We have the rotational inertia of our ball times its angular velocity at the finish, plus the rotational inertia of our disk times the angular velocity of our disk at the finish. But we just talked about how since our ball sticks to our disk and they are now traveling around in a circle as one unit, because they stuck together, they have the same angular velocity, right? So I'm going to factor this out because I know that this and this are exactly the same. So I'm going to pull them out of my terms and have them out at the end here. So this is just the rotational inertia of my ball plus the rotational inertia of my disk times my final rotational velocity, my final angular velocity. So now we have m times r, mass of my ball times my velocity plus mass of my disk times the radius of my disk squared times my initial angular velocity. Okay, now we have something really gross and a lot of letters on our board. Go us! But thankfully we're now almost at a place where we can start plugging in values and simplifying this down. The only thing that we have left is to write expressions out for our our moments of inertia. The moment of inertia of our ball, well, it's just a point mass. This is just mr squared. I'm just going to write this in line here. The mass of our ball times its radius squared, the radius of the disk squared, because that's the distance between our ball and the axis of rotation, plus the rotational inertia of our disk, which is 1/2 the mass of our disk times the radius of our disk squared. Okay, now if I wanted to, I could just divide both sides by all of this gross stuff that I have being multiplied by my angular velocity and move it over here, and then I would have mrv plus 1/2 mr squared omega divided by mr squared plus 1/2 mr squared. But I got out of breath just saying all of those letters, and that would look really, really gross. So instead, I'm just going to start plugging in numbers here. You absolutely could do that, and honestly, if I was doing this on my own paper, that's probably what I would do, is just keep everything as variables and then plug in numbers at the very end. But sometimes letters are scary, and also I have to say everything that I write down, so I'm just going to start plugging in values here. So the mass of our ball is just 5 kilograms. Our radius is just 0.4, and our velocity is 12 meters per second. The mass of our disk is 15 kilograms. Our radius is still 0.4, and that's squared. Our initial angular velocity is 45 radians per second. Then we have that is equal to the mass of our ball, which is 5 kilograms, times our radius squared, which is 0.4 squared, plus 1/2 the mass of our disk, which is 15, times the radius squared, which is 0.4 squared, times omega. Final, I can start plugging these things into a calculator. I get that this is 24. I get that this is 54, the second term here, and then I get on the other side of my equal sign is equal to 0.8 plus 1.2 times my final angular velocity. Whew, that was a lot of math. But all that this is my initial angular momentum of my ball. This is my initial angular momentum of my disk. These are my two moments of inertia of my ball and my disk respectively. And this is my final angular velocity. And so now we are finally in the home stretch. We can combine these things. 24 plus 54, oh goodness, do I know how to add, is a number. Let's see, let's move some of these things away. So we have 24 plus 54 is equal to 0.8 plus 1.2 omega final. 0.8 plus 0.12 is just 2 omega final. This is 78. That, so we divide both sides by 2. And now we are at the end. We have found that our final velocity is 39 radians per second is equal to our final angular velocity. Okay, that was a lot, but a quick check. Our initial angular velocity was 45 radians per second. Now it's 39 radians per second. That feels a little weird. Didn't we think that it was going to be speeding up? Well, yes, kind of. We have more we have the same amount of angular momentum. Oh goodness, we do not have more angular momentum. But because our system now consists of both the hoop and the ball, we have a larger rotational inertia. So because we have more resistance to spinniness, that is all now trying to spin, even though we had this extra thing come in and give us a little kickoff, because our rotational inertia increased by so much, our angular velocity actually decreased. So that was a lot. Thank you so much for sticking with me through all of that. It was a lot of math, but just break it down into all of its steps, and it really just comes down to the conservation of angular momentum, as so many things do. So y'all are troopers. Thank you so much for sticking with me through all of that. If you found this video or any of our other videos to be helpful, please let us know. We read every single comment, I promise. And if you have any questions, please let us know those too. All right, thanks for sticking with me through all of that, and happy physicsing.